so we're going to talk about today then. In 7.3, we're going to talk about rotations. Remember, we talked about, if we go back a couple days, the other day we talked about what it means to be an isometry, a rigid transformation. And then we talked briefly, we introduced the three different kinds of rigid transformations or isometries. Now what are they again? What are the three? What's one of them? Okay, translation, reflection, and rotation. We talked about reflection, so that one's in the bag. We're going to talk about rotations today and translations. Okay, so we'll get the other two. All right, so okay, so rotations. Now, we've already mentioned this stuff a little bit. There's a little bit of vocabulary here, but it's stuff we've essentially already dealt with. We know that a rotation is a transformation in which we take, the way we talked about it, we took a transparency, put a tack in it, and then rotated the transparency. So everything written on the transparency got rotated with the transparency. We call the place where the tack went, that's the fixed point. That's the center of the rotation, okay? And every place else is going to get pivoted around that. So if we look at a couple examples here, if we're going to take a rotation about point P, we're going to rotate it through X degrees, okay? Then every point that starts off in the pre-image is going to get rotated into the image. For example, if Q is a point in the pre-image, then that's going to get rotated to its new position at Q prime. It might look like this. Okay, so there's Q prime, right? Notice what it did. We can just see that it started there and it got rotated over to there, right? P, or R, sorry, R started there and rotated over to there. Now, we briefly mentioned this the other day. Which point moved through a greater distance in that rotation, Q or P? Or R, sorry, Q or R? Q did, right? And what was the reason for that?
Because it was further from P.
Yeah, it's further from the tack. The further you are from the tack, the more you get moved during a rotation. Just like on a merry-go-round, if you're on the very edge, you're going around pretty fast, right? You're making big circles. If you're in the middle of the merry-go-round, you're just barely moving at all. You're just pivoting around a point. You're not covering much ground. And it feels different. You know, on the outside, definitely feels different than being on the inside. Now, which one gets rotated through a bigger angle? Q or R? Or is that a dumb question? What's the real answer to that? Same angle, right? They both get rotated through an angle of, I guess, 60 degrees in this case, I guess is what we're saying it was, right? They both are going to get rotated by 60 degrees. It's just that the further you are away from the tack, the bigger distance that involves, right? But the angle is the same. For a rotation, every point gets rotated through the same angle. That's what it means to be a rotation. Okay, so what if the point that we're talking about, what if Q is on point P? If it's on the tack, then does it move at all? If the point that we're rotating is actually on the tack, if it's on the center of rotation, does it move at all? No, it ends up staying in the same spot. It just pivots, right? Does that make sense? Like if I'm on the very center of the merry-go-round, if I'm on the edge of the merry-go-round, then there's the center. I'm going to go through, I'm going to start there and end here, right? But if I'm standing in the exact center, while everybody else is going around the outside, I'm just doing this. So after we rotate through 60 degrees, have I changed my position? No, same spot, right? So in that case, if Q were a point that were on the center, Q and Q prime, the pre-image and the image would overlap. They'd be the same point, wouldn't they? Right? Just like we said yesterday, what if we're doing a reflection, we're folding the paper? If the point starts off on the axis, on the crease, it doesn't move, does it? It ends up getting mapped right back to itself. That make sense? So this is like, it's similar. I mean, there's an analog there. If the wet ink is on the crease, when you fold it, it just doesn't single dot still. If the point is on the center of the merry-go-round, it stays put. Just pivots is all. Okay? And of course, we could rotate in either direction. We could go clockwise, or we could go counterclockwise. And we get the same kind of thing happening, Bill. The rotation still has the same characteristics, just opposite direction. Okay? Questions on that so far? Does that make sense? Okay, just some terminology. All right, so Theorem 7.2, big theorem, rotation theorem. This is a long one. Not. That's all it says. Rotation is an isometry. We already knew that, right? An isometry means what again? Yeah, metry, that means measure. What's iso mean? Same, yeah, same measurement. So everything stays the same. If we rotate something, we know, if we rotate an object about a tack, about a center, it stays the same. All the angles in that shape would stay the same. All the sides would have the same lengths, etc. It's a rigid transformation. Okay. All right. There's three different. If we want to illustrate what the different kinds of rotations could look like, I don't think this is really that important, but we'll just take a quick look at it. If we're starting with a segment, let's say we're starting with segment QR, blue segment QR. Well, one thing that could happen is if we're putting the tack in at point P, if that's the center of the rotation, the case we just looked at previously was one where Q and R and P were non-collinear. In other words, they were not collinear. Now remind me real quick, what does it mean to be collinear? What's the co mean? Yeah, it means, same line, doesn't it? Right? The co is same, linear means line. So we know that collinear means if 3 points are collinear, then all three of those points can be drawn on the same line, right? If they're non-collinear, they're not. So for example, Q, R, and P, they don't line up on a single line, do they? And if they don't, then that's what the rotation looks like. What we just looked at in the previous example, right? Okay, this is rotated around to there. Okay. Now, what if they do line up all on the same line? No big deal. Then, if Q, R, and P are collinear, then that entire line just gets rotated around P. No big deal. I'm honestly not even sure why textbooks always make this distinction. It just seems pretty natural. What if point R, what if we stretch out this blue segment so point R is actually on the center where the tack goes? What's going to happen? It's going to stay the same. It's just going to pivot around that one point. Right? So it'll look like that. No big deal. Right? R and R prime would end up overlapping then because they're on the tack, on the center. Okay? All right, so what about this then? Now what's going to happen if let's go ahead and take a random quadrilateral, A, B, C, D. Okay, and this is, so we're going by ones, 1, 2, 3, 4. Now what's going to happen here if we want to take this thing and we want to rotate it through a nice convenient 90-degree angle? Because we do that a lot in math. We do a lot of 90-degree rotations. And you'll see examples of that later on. Even Algebra 2 will talk about this a bit, and even more so when you get beyond that. What can we expect to happen there? Now, technically, if we're going to rotate something, the tools of geometry would be, in this case, a protractor and a compass and a straight edge. But that's not a very precise way of doing things. Can we, instead of having to draw this thing manually, can we make a prediction where this blue quadrilateral is going to end up if we rotate it 90 degrees counterclockwise? Now, I want you to think about what happens here to a 90-degree counterclockwise. What happens to all of the relative directions, the positive x direction, the positive y direction. What's going to happen to those if I rotate them through 90 degrees counterclockwise? Let's take a quick example. What if we've got like this? What if we've got, I want to do this. So there's, wrong color. So there's the positive y-axis to start with, right? Let's do this. If this is going to work or not, let's see. there's the positive x-axis, right? Let me label those. So there's x, there's y. What's going to happen? If I want to rotate that thing about its center, right? I want to rotate that thing about its center. In what direction, 90 degrees counterclockwise, in what direction is the old positive x-axis, positive x direction going to point? Yeah. In what direction is the old positive y direction going to point? To the left. Aha. Okay, so let's try this. I don't know if it's going to work. I'm just kind of making this up as I go. Oh, it is going to work. Okay. So there we go. Right? Now, there are the originals. There's x and y that we started with. If we stop here, okay, so we stopped after our rotation. Now, we know that this really, that this really is the positive x direction, isn't it? Right? And this really is truly the positive y direction. So if I want to think of what's happened to a point, its old x coordinate has now become its new y coordinate, hasn't it? Its old y coordinate has actually, it now points in the opposite direction of the x-axis, right? So couldn't we say something like this? We're going to start with, if we want to know what's happened to that point, its x position is actually the opposite of its original y value, right? And its y position is what used to be its x position, right? Does that make sense? So make a prediction for me. If I start off with, let's say I started off with the point 5, 2. 2, 3, 4, 5, 1, 2. So there's point A with coordinates 5, 2. If I rotate that thing 90 degrees counterclockwise, like so, what are the new coordinates going to be? What used to be, yeah, right? The new x coordinate is going to be the opposite of what used to be my y coordinate. So 2 becomes, a y value of 2 becomes an x value of negative 2, right? Is that making sense? Let me move this a little bit. I'm going to run into my point. Oops. Now, what about my new y coordinate? That's my old x coordinate. So positive 5, right? What used to be x now becomes y. Okay, could we have made that a little simpler? Kind of. Just think of it this way. If my directions now, could we summarize that? If we wanted to explain this to your younger brother or sister, I think this gets a little bit easier. What it used to be, if I wanted to describe how to get to this point, that's what coordinates do. They say the roadmap is 5 to the right, 2 up, right? So the 5 to the right part, if I twist this thing 90 degrees, actually becomes a 5 up part, doesn't it? Right? What about the 2 up? Whoops. The 2 up. If I twist this thing 90 degrees, that arrow now is going to point left, isn't it? I can just visualize that. See what I'm saying? See how we can do that? Yeah.
And this only works if you rotate it from the...
It only works in 90-degree increments, right? That if I had rotated this 37.9 degrees, oh man, that's going to be weird. 37.9 degrees is going to be, then I'm going to end up with something kind of, up here, and that's going to be a little strange. Yeah.
And the point has to be from 0, 0, right?
Yes, we're rotating about the origin in 90-degree increments. Now, would you agree if I had rotated this thing clockwise instead of counterclockwise, it would have changed, right? If I were rotating this thing clockwise, instead of counterclockwise, then what used to be traveling to the right becomes what? Down. Okay. So right direction becomes down when I rotate the whole graph. So I'll go down 5. And then what used to be up, if I rotate the whole graph, becomes what? To which direction? Yeah, to the right. So I end up with that, right? So my coordinates would now be, if I did a clockwise rotation, I'd end up traveling in the x direction 2, and in the y direction down 5, so negative 5. See how that works? So you just kind of have to play that little game. When you're doing 90-degree rotations, increments like that, you just want to ask yourself, okay, this becomes what? That. Okay. This becomes, and you can just play the little arrow game. And that way you can get the coordinates without having to pull out a protractor and a straight edge and all that stuff, right? We don't want to do that. We want to avoid that. Okay, so we end up then, would you agree we end up with something like that? Right? What, for example, A used to be over 2 and down 2. Now it's going to be up 2 and right 2. Right? Because over becomes up, down becomes right. Okay? We can do that for each of the 4 points, and then just connect the dots. Okay? You'll do a few of those on the assignment. Okay, no big deal, really. Okay, what about, let's look at a couple other things here. Okay, this is kind of interesting. I always like this one. Okay, now watch this. This is, you wouldn't expect this maybe. If we do a double reflection, okay, so look what we're doing here. We're starting with the blue segment AB, okay, and we're going to reflect that in the line K. In other words, we're going to reflect it over the line K. So K is going to be our fold. We're going to draw segment AB in wet ink, fold the paper on line K, and create an image. Right? We started with the pre-image AB, and we get the image, the imprint, the ink imprint, A prime, B prime. Right? Okay. Now we're going to fold the paper again. We're going to fold the paper on M, and we're going to do a second reflection. So I'm going to take this red ink, and I'm going to fold it over M to create the green imprint. So think what we just did there now. The image of our first reflection becomes the what of our second reflection? Pre-image, right? And so why do I end up with double primes here? Yeah, and so think about that. The number of primes keeps a tally for you of how many times you've done a transformation in math. That's kind of slick. So I went through 2 transformations. Now, do you see something else? Could I have maybe skipped the middleman there? Is there a single transformation I could have done instead of those 2 reflections that would have mapped my original pre-image to my final image? Yeah. Couldn't I have rotated the whole thing? Look at that. If I took this blue one, look what happens here. This is really slick. If I take this blue one and I rotate it about the point where the 2 lines of reflection cross, the 2 folds in the paper cross at point P, right? So if I rotate about point P, if I go something like, that's a pretty bad arc, but you get the idea. And I rotate B for the same angle, I end up with, B's a little closer, so it doesn't move as far. Boy, I drew that pretty terribly, didn't I? Let's try that one time. You can see it better. There's the angle that A goes through. Here's the angle that B goes through. Same angle, different distances, right? I could do a single rotation and get from the blue to the green in one fell swoop. Okay, now how far, here's the interesting part, how far would I have to rotate it? When I folded the paper, I had the fold on K and the fold on M, and if we measured the angle between those, let's say it's X, how far is my rotation going to have to be, I suppose? More than X, right? Twice as much, in fact. We're going to rotate it through 2X, and it's the same thing as the double reflection. How about that? All right? Let's see here, so... Right? The angle rotation of 2x degrees is the same thing, where x is the measure the angle between the 2 lines is the same thing as a double reflection over those 2 lines. How about that? Okay, we'll come back to that. We'll see that again in a very extreme case. So let's use that once. What happens then? How about this one? If we're going to reflect the original pre-image, what is that? It's going to be RST, over the line K to create the red image, and then use that as the pre-image and fold that over line M. Okay? That's the same as what? That double reflection I could describe as what single transformation? What do you think? Okay, a rotation of 120 degrees. Now we got that part's right. We got to add a little more information. A rotation of 120 degrees in which direction? Which kind of rotation? Clockwise or counterclockwise? Clockwise. About what point? Where did we put the tack when we rotated it? Point P. Good. Okay, it's a rotation, a counterclockwise or clockwise rotation, sorry, of 120 degrees about point P. Gets us there in one single transformation instead of two. Make sense? Okay. 120 degrees about point P. Okay? It's pretty cool that it does that. Okay, last part of this then, the rotation stuff. We talked the other day, remember, about line symmetry. And let's take a couple examples. We looked at something like maybe this shape. If I draw... I didn't draw that very well. We'll pretend it's a good drawing. You think so? Oh, thank you. Thank you. How many lines of symmetry does that have? One. Correct. How come? Explain why. Down the middle. Okay, so I'll draw here's the line of symmetry. What does that mean that line of symmetry is vertical line right down the middle? Well, what's one way of describing why? Okay, it's a reflection. I could reflect the left piece onto the right piece. What about if I think of it in terms of folded? Well, it does that too. Yeah, it's going to bisect a bunch of stuff up there. But if I think about that in terms of folding a piece of paper, what happens when I fold that shape along with that? They overlap perfectly, right? That's the only way I could fold the paper so that the shape folds on itself and overlaps perfectly, isn't it? Any other fold I make, it's not going to line up, right? Now, what if I make one slight change here? What if I do this? What if I say, okay, let's make this bottom one instead maybe look like this? Now, how many does it have?
3.
3? Somebody sees 3? That's pretty good. I see 2. There's that one, and where's the other one? Horizontal, right through there. I could fold it that way, and it would work, wouldn't it? That's it. Okay. Now, the more line symmetry it has, the more ways I could fold it, right, and have it line up with itself. And recall that we said if we took regular polygons, the more sides on the polygon, the more way that I could fold it, or I could fold it on itself, right? We took a square, and then we took a hexagon, and the hexagon had lots. Remember those pictures? What was our ultimate limit there? What was the most symmetrical two-dimensional shape that we could fold the most ways and have it overlap? Circle. We could take any line through the center of the circle and fold it, and it's going to overlap on itself, isn't it? So circle was the clear winner there. Okay. Well, let's see what happens with rotational symmetry. Okay, with rotational symmetry, now for an object to have rotational symmetry, what that means is if I put a tack in the exact center of the shape and I spin the transparency around that tack, can I spin it less than one complete turn and have it overlap? Right? The more times I can do that, the more ways I can get this thing to overlap before I get back to my original starting place, the more rotational symmetry it has. So what about a square? How far do I have to spin a square for it to overlap? 90 degrees, right? If I spin this thing, there's what 45 looks like, right? That's not overlapped yet, but if I spin it through 90, aha, now it works. Now it overlaps perfectly, doesn't it? Okay. And then I could go another 90 degrees and another 90 degrees. So in 90-degree increments, that one's going to overlap. That's pretty symmetrical. Okay? What about that octagon? Is that more or less symmetrical? If we're talking about rotational symmetry. What do you think?
I had a question about the split.
Say it again.
I had a question about the
Oh,
split.
sure. Okay.
Is it 4 symmetrical rotations because of the 0 degrees count or not?
0. So you could. How many times could you make it overlap between 0 and 1 rotation? You could make it overlap 4 times.
Yeah,
you
0
would.
degrees count.
0 degrees. Well, no, that's the starting line. Then we'd go through 90-degree increments.
So it's 3.
Yeah.
Okay.
We can make 3 discrete switches. Right. Okay. So now, what about an octagon? Is that going to be more or less? Have more or less rotational symmetry?
Less.
It's going to have more symmetry. I know why you say less. I can tell them saying less because you go through a smaller angle. Yeah, but that means it's more symmetrical, right? I don't have to spin it as far. How far does this one have to spin? Instead of 90 degrees, how far could this one spin? 45, sure. I could spin this thing through 45, 90, 135, 180. Does that make sense? Okay. And so it's got a lot of symmetry. What about a parallelogram?
Have to be 180.
It has to be 180, doesn't it? If I stick a pin in the center of that thing, I got to spin it clear around before I get it to overlap. So that has less symmetry. What about this bizarre trapezoid?
360.
Yeah, that one has no rotational symmetry because I have to spin it one. It's cheating to spin it all the way around once. Of course, it's going to overlap, right? So that doesn't count. It's got none. Yeah, I can't spin it anything less than a complete rotation. Now, what about this guy? I think it's kind of cool. This company here, they're trying to come up with. If anybody's going into graphic design, this is actually something that you would study. No kidding. You'd study the symmetries of stuff because a lot of times things that are more symmetrical or more symmetric are more pleasing to the eye. So these guys, they're calling their store Ozone. They want to come up with some jazzy logo that's got this kind of symmetry where you can rotate it. Now, how much symmetry do you think that one has?
You turn it 180 degrees.
180. Yeah, let's watch this. I actually copied this, and we can see this thing in action here. So if I grab this guy, now watch this. If I spin it 180 degrees, hey, look at that. Looks the same. How about that? So that's pretty good. Could they do better? Well, maybe. How much could I spin this one? 90 degrees? Right?
It says.
Right? Just one more time. That's kind of fun.
Whoa.
Okay, how about that? So that one's more symmetrical. Yeah? They are. They're graphical wizards, aren't they? Okay.
That's awesome. Like you
Question?
letters from.
Question.
I don't know.
Well, okay. The only question I was asking about these two logos is if they're trying to come up with a logo design that has rotational symmetry.
I was looking at. I thought I was like, how did you put it? But I can see that.
Oh, this one? Yeah. Okay. So this one had 180 degree, right? Had to spin it. This one only 90, so this one has a little more symmetry. Okay, so next issue. Might as well. This one's really related. It makes sense to do it now, but then we got it out of the way, and you guys can just go practice this stuff tomorrow. Okay, the next issue is translations. Translations are the easiest to see by far. They're just sliding or gliding, we say in geometry a lot. So a translation just does this. I'm going to take this original pre-image and just glide it, take the whole transparency and slide it without twisting. I'm going to slide it in a straight line some distance in whatever direction I choose. Okay, so that's a translation. And now we know there are some properties of this that we could talk about. Now, does this make sense? Here's kind of the geometry part of describing a translation or a glide. Wouldn't you agree that if I'm starting with segment PQ and I'm going to slide that whole thing in tandem up to P prime, Q prime, then wouldn't you agree that if I'm going to track the path of the two endpoints, what if I track the journey from P to P prime and from Q to Q prime and compare those two segments? Doesn't it make sense, of course, that they have to be congruent? If we're going to move this thing and it's not going to change its orientation at all, it's not twisting, don't both of those have to obviously move the same distance? So those two sides are congruent. The lengths are the same. Doesn't it also make sense that they're going to have to move in the same direction? The whole thing is being moved in unison or tandem in a single direction. And so, of course, those two segments would also be parallel. I mean, that just stands to reason. That's the geometry way of kind of nailing down what we just said about a glide. Okay. So it is an isometry. Now, how do we there's just a picture, right? So one thing we see here, this just illustrates the idea that if I start with the green pre-image and end up with the purple image, notice that when I glide it or translate it, it doesn't rotate at all. The rotational orientation stays the same. Okay, this is the part that I think is really interesting. Yeah, Pac-Man. Now, I want you to think. I got to go back for a second. This is you got to really pay attention to this, but it's very cool if you can see this relationship. And I hope I don't mess this up. It's hard for me to draw this on here, but I'm going to give it a try. Okay, let's go back to that idea from the last section. Remember we said that if I take two lines of reflection and I do a double reflection, that's the same as a rotation, right? Everybody agree? So if I take, for example, I'm going to try to draw this. Don't laugh at me. It's probably not going to be very good. If I take, here's one line, okay, and here is another line. Okay, and let's just take a little shape. I'm going to draw something easy. How about if I take the shape that looks like, let's take that little rectangle. Okay? Now, if I reflect that over the first one, it ends up about there, don't you think? Does that seem reasonable? And now if I reflect it over this one, it's going to look kind of like this. There, maybe like there, kind of like, so that one's going to end up about there, so something kind of like that. Close enough? I mean, I probably should have been further away. But you get the idea, right? So we could replace that whole shebang with a single rotation about the center, right? So we could just do something like that. Agreed? Okay. Now what happens to that situation that we just talked about if I make this angle smaller, which I can accomplish in this way? Now watch what I'm going to do. Let's get rid of all the drawings for a second. And let's take this line and let's drag him way down here. Okay. As that angle gets smaller, what happens to the rotation? Right? If the center is clear down there, right? And so let's make a point so I can draw it more easily. We start right there. We reflect it once. We reflect it again. Now notice this time that this arc, that doesn't look as bendy, does it? Doesn't look as curvy. Agreed? That last one, you can see it was really a pronounced curvature. This one's starting to not look so curvy. What if I take this point of intersection, and instead of making it 1 meter away, what if I make it like 20 meters away? So now you can't even see it. It's way down probably in the first floor or below. Now, doesn't that do... See what I'm saying? So now what's going to happen to this red guy then? This red guy, isn't it going to start to look kind of like that? Because now they're not going to meet until way down there. What's happening to those lines as the point of intersection? Yeah, they're getting to look more and more what? Those parallel. They're starting to look more like parallel lines, aren't they? And if I reflect something now, if I go clear down there, so it's 20 meters away, does that look about right? Say those might hit down there at about 20 meters. Now watch this rotation. I'm starting there, reflecting it over to there, reflecting it over to there, oops, to about there. I mean, you can hardly even tell that's a rotation. It's starting to look more and more, instead of a rotation, like what? A translation. Okay, now here's the weird part that the book doesn't talk about. What if we're gonna let this go to a ridiculous extreme? Instead of having these things cross 20 meters away, let's make them cross 20 miles away. Oh, let's not stop there. Let's have it cross at the sun. We're going to have it cross 93 million miles away. Can you even tell that these aren't parallel anymore? You would need, there's nothing that would work, there's no tool that people have made. Maybe an interferometer. Maybe we could create some kind of a laser interferometer that could measure the very slight differences in those distances. But we're talking about fractions of the width of an electron now. I mean, they're really small. Let's even go further than that. Let's push this intersection out to infinity. Now, infinity is not a number, right? Infinity just means without limit. So, two lines, now this is a little strange, and just bear with me on this, a little strange. If I push the intersection of two lines out to infinity, what have I actually done to those two lines? I've made them truly parallel, right? Parallel lines never cross, right? That's our definition. If parallel lines never cross, isn't that the same thing as saying they cross at infinity? Because you never get to infinity, right? Weird. So if I do that, if I push that intersection out to infinity and I make these lines parallel, could I see any curvature anymore at all in this arc? No. It would become perfectly straight. Those 3 points would become collinear, wouldn't they? And then, Sue, what actually has that rotation truly become? A translation. Yeah, how about that? So we can say that. We can take that very same relationship that we talked about last section, and we could say, okay, well now instead of having these two lines cross, let's let them cross at infinity. Let's let them become parallel. And now, instead of replacing the double reflection with a single rotation, we replace it with a single translation. How far? If the distance between these two lines is x, how far do you suppose we have translated the object? 2x. How about that? Yeah. Okay. It all kind of comes together, doesn't it? Okay. So there's our theorem. If the spacing between the lines, two lines are parallel, we do a double reflection. If the spacing between the lines, they call it d, is d, then the translation is 2d. Okay? I wonder if that's a pretty good place to stop. I think it is. I don't think I'm gonna do this. I think we'll wait and we'll do that at the beginning of the period, and then we'll take a day and a half, almost 2 days in the lab to work on this stuff.